Alright, this is going to be my final video on Frege's Begriffsschrift. So, the first video I talked about the purpose and relevance of this whole thing and why he did it, why he did his conceptual notation. The second video, which I did today, was pretty much just like talking about the second part, which is some judgments of pure thought. So if you want to get like a general understanding of his conceptual notation, I would go back to the second video. This video is going to be talking about the third part, which is the general theory of sequences, which is a good bit more complex, because he does make this more complex because he says that making this more complex shows the advantages of his conceptual notation. But it is pretty easy to understand because he shows that when he does a very complex little notation like this, he shows exactly what it means in his general conceptual notation. And I have these arrows here. Those are not a part of his notation. I just did that to show which way each part of this means, or shows where something is going within the sequence. So, as I talked about in the last video, with this kind of notation, we go upward. We read it upward. These are supposed to be in Gothic fonts, or Gothic typeset. So I can't really do that, but it looks something like this. This one right here is what I'm trying to kind of illustrate. This. So, like I said in the last video, this little concave means generality or universality, and this is similar. At least if we're talking about this one, similar to saying this is similar to the universal quantifier. This is, but for all A, if f of d, then if f of dA, then f of a, and this is equal, basically the same thing, to this. We are talking about a sequence here. Now, kind of explain his translation to English of this. It's if the proposition that D has property f, whatever D may be, it can always be inferred that each result of an application of the procedure f to B has the property f. Then it says the property f is hereditary in the f sequence. So it's talking about various different things and showing how the property f is hereditary among them in this sequence of certain things that are talked about have that property f. So basically saying that whenever we see this, it's equal to this. So we have the symbol delta, the uppercase delta. This is the uppercase. I did that terribly. That's the uppercase delta, and this is the lowercase one. Delta, and we have alpha, and we have f of alpha, and we have f of delta alpha. Where it's saying that we're talking about the sequence from delta to alpha. We're talking about the sequence of delta alpha to alpha, because we start with delta, as you saw here, and we're showing how the property f is hereditary in the f sequence as we move towards alpha and towards other things as well. So what else? I wanted to kind of do a couple things in this book, kind of show what it means, and it does get a bit more complicated. I'm not going to go through the whole entire thing. I just want to show like one more complex symbol like this, and show entirely what this whole thing is. And then, this is what I'm going to do. Page 171 top. Okay. Now that I've done this, we're going to show how this would be, how that symbol that I just had there would be evident in something else. F of f of y, f of x, y. And this one my finger's getting dirty, okay. Delta 2 alpha f of alpha f of delta alpha. Then we have f of x, f of x, y, and then the top f of y. Okay, so we have this complex symbol, which is amongst something which this is going to get complicated since we have a symbol like this, which is a whole thing on its own. It's a whole thing on its own. So we have down here, because since when we do this we go bottom upward, we have I would think of this as one element and then this as one element, and possibly connect the two with either a ampersand or a conjunction when I'm thinking about this in terms of a more sentential logic kind of setting. I mean, even though we have generality. So we have, for all a, f of x a, then f of a. So as you can see, when we have something like this, or this, or this, we are showing that as we go from things like x to x of y and then to y, as we move down more things, we are showing that the properties f is hereditary. In that we are showing a sequence. A sequence in that a bunch of different things that all carry the same property. That's why this is all important, I guess. That's what he's trying to illustrate, and he's doing this because he's trying to show the advantage of such a notation as things get more complicated, because if things get more complicated and he has this better notation, we can do better proofs and do better things with it, and more complicated things, and just a lot better things all around, really. So we have for all a, if f of x a, then f of a, and if f of x y, then f of y, and then we have this big symbol, which of course shows that if we have f of delta, then f of delta alpha, then f of alpha, then this is just saying that if we have this showing that the property f is hereditary in delta to delta alpha to alpha, then if we have the x which has property f, then xy which both have property f, then y has the same thing too. It has the same, which is saying that the f sequence, the f property f, is hereditary. It's whole thing. It goes through everything. else here? Number 26, or section 26 on page 173. And now this one, which is we're gonna have another symbol, which makes things even more complicated, which is interesting, I think. We're gonna have another little, like, I guess, something which is we have F. The fancy F means that pretty much that we are talking about something that ranges over more things. It's a higher order, and that's just pretty much the way I would explain it, is of a higher order. And we have the A and that concave. And down here we have our previous little symbol, or a little notation, which was complex beforehand. F of alpha and then F of delta alpha. And that comes up to F of X alpha A. And then the fancy F of A, then F of Y. So we have this notation, which means that given for all F, it's a higher order property, and it can range over more things. So we had this one, which we know, which we recall. We have these two things, which is what we're talking about. This is two different kinds of things, or different things, I guess. And we have, basically, again, what this means is that we have delta alpha and alpha, which means that from delta to delta alpha to alpha, the property F is hereditary. And if that is the case, then for all A, if F of X A, then F of A, and then F of Y. So it's just showing how, as we move towards different things, the property F is hereditary in the F sequence. So we have this, which is equal to this more complex thing. I forget what that symbol is called, but it's a Greek letter. Wish I could look that up. Okay. Perhaps I'm trying to think of what this is called, but it doesn't matter. I know this is beta. I forget. But again, what this is saying, that it's because in a function of x and y written down in detail these letters because they'll occur outside. Where does he give the what this is kind of saying is that it's still a same kind of sequence. Is that I'm trying to think of what that I'm trying to think of what he was saying. It's from this Greek letter to beta, and it's saying that y follows x in the F sequence. it's still saying that the property f is hereditary, and as we are going from different kinds of objects, it's still the same thing, but we're going in, I guess, more complex fashions. There's a better way to explain it, but this is kind of getting more complex. But the whole thing to me about this is that this is the same thing as this, and that x follows y in the f sequence, and that it's just kind of the whole thing is it's a sequence, and that in that as we go from different kinds of objects, the same property ranges over all of them as we go towards from x to y. Goes in that direction, and in that direction. Y follows x in the f sequence. What else did I want to do? Page 174. And what this is saying is that if from the two propositions that every result of an application of the procedure f2x has the property f, and that property f is hereditary in the f sequence, it can be inferred, whatever f may be, that y has the property f. So then, finally, I want to do one more thing, and then I'll be done with this, because I just think it's interesting to note the complexity. All right. Top one is f of y. This one is f and then the next one is that one we had before. Alpha, f delta alpha. And the last one is f of x. And I want to show what this is doing, and then make a note on what this would be if we didn't have this. If we didn't have this kind of notation, how this whole thing would be, and how horribly difficult and how much effort it would take to kind of symbolize this if we didn't have such a notation. Now, the way I would do this is if this, then this, then this, then this, and kind of link these up with horseshoes. So if we have f of x, now when we have a function, it's just saying that x has the property f. Now, what the whole thing is doing, it's showing that from x to y, among all these things in the sequence, that the property f is hereditary, and that everything that is part of this carries within the f sequence. It is a sequence in that everything that is a part of it carries the f property. So if we have f of x, then we have from f of delta to f of delta alpha to f of alpha. And then here we have that x follows y in the f sequence. This way, and this way, and then this way, and this way. Then y carries the property f. Okay, and this gets really complicated. Just want to show you, just in the book, one more thing as to how, like, crazy it gets. Like, now just think about that. Like, imagine how horrible this would be if we didn't have this. Because if we didn't have this, this would be a ton of symbolizing within sentential logic. This would be horribly long. Well, you know, this is about a proof, of course. Now, if you know about proofs in sentential logic, that how how difficult those are as it is. And personally, I think that the proofs get easier as we get into quantificational logic, which is the logic that Frege helped create. Frege helped create it like as if we had something like this, the concave thing. Just like this would be the longest proof, and I can see how we can make gapless proofs with this. And I guess it kind of shows to me how if we didn't have this, I mean, and we were doing just like these whole huge proofs, then they would be even worse and even more like this would just be the worst thing possible. So if you think I left something out or didn't explain something correctly, it's clicking in my head, and it doesn't always enable me to kind of explain it that well. So if you need help, or you need help in understanding this, or if you think I explained something wrong or botched something, whatever, please comment below, because I'd love to hear from you and to discuss with you. Also, just because whatever you want to comment, just do it. So whenever you comment, I get an email, and if your comment is constructive, I always respond.